Welcome everyone to Science Society, and of course, a special welcome to you, Molly. And before we start, let me give the audience a short introduction about you, and then we'll also ask a few interview questions before we dive into your research. So, Molly Burkmar, she is at the Institute of Cosmology and Gravitation at the University of Portsmouth. I hope I'm saying it right for the UK. She is researching bouncing cosmologies there, and she did her undergrad studies at the Aberystwyth University, where she then later moved on to the University of Portsmouth, where she is right now, and the physics, astrophysics, and cosmology. And she did her master's project there, also focused on inflationary cosmology, which was already really interesting. And so please read it. Check her out on her LinkedIn website. There you can read all about it and summaries about it. And now we will soon talk about the current research that was just published. And Molly, how did you basically discover in your life that you want to become a researcher? Was it something that you always wanted to do? Was something special that kind of sparked your interest? We would be really curious to hear about that. Thank you.
Yeah, thank you for that introduction as well. So really my interest in, I guess, space in general actually did come from my dad. So he's a bit of an amateur astronomer. And when me and my sister were younger, he would take us out and watch meteor showers. And yeah, I think that's kind of what really started my interest. I think as I got a bit older and, kind of start looking at science a bit more, anything to do with space was always my favourite. I remember going to a science centre on a school trip, and I came back and I said to my dad, we have to go again. And so we went the following summer back to the science centre again. And I just remember going in the planetarium, and I was like, there's just so much out there. And then, I think, again, as I went through school, I took physics kind of to the furthest point in my secondary education, and again, just space always was my favorite topic. Anything astrophysics was the thing that really sparked my interest. So that's really why I decided to do it at university. And then I think really from there it was a case of kind of a convoluted story, but just for background, I wasn't actually predicted a good enough grade in physics to go straight onto a degree course. So that's actually why I was in Aberystwyth for a year, because I was expecting to do a foundation year in physics first. We did a test in the first week, and I had a flatmate who was actually straight onto the normal undergraduate degree, and I actually had a higher mark than him. So I went to my lecturers and were like, please, can I move on to the first year of the course, because I don't think I'm not sure I'm going to learn a lot from the first year. The test was really for the first year undergraduates that were straight on the usual course, not the foundation year, just to recap. And I think I really kind of knew then it was cosmology. So it was kind of looking at the universe as a whole that really was the thing that made me the most curious. So then that's when I moved to Portsmouth, and I really think that hearing my lecturers speak and kind of hearing what they did, it was always it was always cosmology. It was always kind of these big kind of universe questions that really made me really made me excited about research in general. And then I think, by the time I was going into my last couple of years of university for my undergraduate, I was like, I need to apply for a PhD and see if I can carry on researching, which thankfully they wanted me to do. Thankfully they wanted me to stay as well, and I wanted to stay. So yeah, that worked out well.
Well, that is wonderful to hear, that you had, this very early on exposure to science, and and that you got along the way people that supported your decision and your passion and interest. It's really wonderful. It's a really happy story, I would say, that worked out really wonderfully. So I'm really glad to hear that, and I think that emphasizes that we should give children the most exposure we can to different subjects, not in all kinds of museums and like actual hands-on experiences, maybe, so that kids can figure out what their passion will be in life. So yeah, you're a perfect example for that. And if you could take us from there, like how you then chose your path, like how did you get to work on this project, and also how did you kind of decide to work in the group that you're in? Is there maybe a story around that, like how this project that we will discuss today came about, and how you kind of chose or got to be involved in it? Thank you.
Yeah, so I guess really it started with my master's project. So my I mean, I guess with the group there in general, I knew a lot of people in the group just because they were my lecturers, and I did a project for my master's on inflation, which I will actually touch briefly on in my talk. But essentially, this is something that happens in the very early universe. And I think from there, I really knew that I wanted to stick with early universe cosmology. So I was kind of fascinated by kind of the first literally the first second or less of our universe. So then really when it came to looking at projects, so I mean I looked at a few different universities, but the project I'm working on now with my supervisor Marco, he had a project advertising this bouncing cosmology, and that's even earlier than inflation. So I think it really sparked from kind of going into more detail in the early universe in my masters, and then I kind of knew that I would most like a project kind of in that area.
Yeah, that's really interesting, and it's also really interesting that the time span something happens isn't really a reflection of how important and how much can be going on, and how much to study, and in like less than a minute. So that is always so fascinating to me, that there are billions of years nothing, like not nothing, but not too much extraordinary happens, and then in less than a minute everything happens. I think that's fascinating. So yeah, thank you for taking the time to share this with us, and we're really looking forward to the presentation. And the link to the slides are pinned on top of the room as usual. Feel free to access them. And Molly, the stage is yours. Thank you.
Thank you. So yeah, I'll kind of talk through my slides, but if anyone doesn't have or isn't in a good situation to look at them, I'll try and explain it so you don't necessarily need the slides, but hopefully it gives some kind of nice visual representations of things. So the results that I'll talk through here that I've been working on were published in a paper, which should be in print very soon, I hope. And yeah, so to start with today, I'll kind of give an overview of our kind of current understanding of the history of our universe, kind of to give an idea of the bigger picture of my research. And then I'll kind of go into the work that I've been doing with my supervisor, Marco Bruni, which kind of then goes into the results of the paper. So the standard model of cosmology is really kind of the widely accepted version of the history of our universe. And really the first thing that this standard model of cosmology needs to do is to explain why our universe is the way it is today. So, and that begs the question, what is our universe made up of today? So if you go to slide 2, you can see a pie chart here, which shows us what observations have told us about what our universe is made up of, essentially. So the first thing that's in our universe, which doesn't actually have a wedge here, just because it makes up like a fraction of a percent of our universe today, is what we call radiation. So radiation is really the term given to particles that travel close to or at the speed of light. So this includes things like the light from stars, and also light from the very early universe. And we call these light particles photons. We also then have ordinary matter, which is shown on the chart, which are things like you and me, our stars, galaxies, planets, and this makes up around 5% of our universe. But actually only about 1/6 of the total matter content of our universe. Most of the matter in our universe is what we call dark matter. And we call it dark matter because it doesn't interact with light, and so we can't see it, unlike ordinary matter that we can see. Now, we're pretty sure dark matter exists due to some things that we've observed. So I thought maybe I'd give you one of these observations just to give you an idea of kind of where we're looking to say that we think we have dark matter. So one of these observations are known as galaxy rotation curves. So this is where people have looked at how stars in a galaxy orbit the centre of the galaxy. So in general, stars in the inner parts of a galaxy are expected to rotate around the centre faster than any stars in the outer parts. And this is because observations show that there's more ordinary matter, so matter that we can see in the inner parts of a galaxy than the outer parts. And kind of more mass means there's a higher gravitational force in these inner parts, which we would think would then lead to these rotational speeds of the stars being higher. However, it's been observed that stars in the outer parts of galaxies actually rotate at speeds faster than we expected. So it shows us that there must be more mass there than we can see. Otherwise, if these stars were rotating at these speeds that we observe, we would expect the galaxy to tear itself apart. So therefore, we think there's dark matter around the edges of the galaxy that we can't see. So that's kind of about 30% of our universe. The last roughly 70% is what we call dark energy. So in a similar fashion to the dark matter, it's called dark energy because we can't see it. But like the dark matter, we see its effects in the universe. And the effect really of dark energy is that it causes the expansion of our universe to accelerate. So this was kind of maybe a surprising observation, as we thought that the gravitational force, the gravity from the matter in our universe, would kind of stop it from accelerating. But in fact, we observe an accelerated expansion. So that's kind of a whirlwind tour of what's in our universe today. The next question then we need to address is really the geometry of our universe. So there are three possibilities for this, which can be seen on slide 3 now. So the top image is what we call a closed universe, and if our universe is closed, it's a sphere. The middle image here is an open universe, where if we have an open universe, it looks like a saddle, so a bit like a horse's saddle. And then the bottom image is a flat universe, and in this case, the universe looks like a sheet of paper. So again, we've got observations that kind of tell us what we think the universe is close to looking like. And actually, observations show us that our universe is very, very close to being flat. It's been argued that the data slightly favours a closed spherical universe, but in reality, all three of these cases are still possible. So then we can really put this all together into our standard model of cosmology. So I show this on slide 4. This is like a schematic figure of the evolution. So if we start on the very left, where that kind of glowy part of the image is, we think our universe started with a singularity, which is also known as the Big Bang. So this is a point in space and time where the density and the temperatures are infinite. We then see this rapid accelerated expansion, which is labelled inflation. So this is where the universe very quickly becomes much, much bigger. And this really is a mechanism that does a few things. So firstly, it's a mechanism that makes the universe become close to being flat, like we observe. So this was really implemented so that we could kind of explain current observations. Secondly, it creates radiation and matter. So at the end of inflation, we end up with a lot of photons, so a lot of these light particles, and then some matter particles as well. So just after inflation, initially we have a universe dominated by radiation, so a period dominated by these photons, and this is a decelerated period in our universe. So at this point, the photons and then the matter particles are all interacting with each other, but the universe kind of expands and it cools, and actually atoms are able to form and the photons are able to spread out around our expanding universe. And this is what's labelled on this image as the afterglow light pattern. So the radiation energy density decreases as the universe expands and the photons or these light particles spread out over larger volumes. As this decreases, we then have a matter dominated period, which is also a decelerated expansion period, where we have dark matter start to clump together and then ordinary matter start to clump to this. And this is what's labelled as the dark ages in the image. So eventually what we get is star formation and then galaxy formation, and then clusters of galaxies form after this point. So this is really the period from the first stars through to the development of the galaxies and planets, etc. And actually I should say, so the at the top I've labelled this slide lambda CDM plus inflation, which is what our standard model of cosmology is. The CDM in the lambda CDM stands for cold dark matter. And this really just means that the dark matter is cold, which means that it moves slower than much slower than the speed of light. So we think it's cold because otherwise it wouldn't cluster on large scales, because it would be moving close to the speed of light. But because we think we see dark matter in galaxies and galaxy clusters, we think it has to be cold for it to actually be able to clump together in the early universe. So then after these formation of galaxies and the galaxy clusters, the matter energy density increases with the expansion of the universe. And then finally today, we're in a period of dark energy domination. So this is what causes our expansion to accelerate. And this is where the lambda in lambda CDM comes in. So unlike the energy densities of matter and radiation, which decreases with the expanding universe, so as the volume of the universe increases, there's basically less radiation and matter per unit volume, the dark energy density is always constant and it's unaffected by the expansion. So in this model, essentially the dark energy starts off as the least dominant component below matter and radiation, but as matter and radiation decrease, then essentially the dark energy eventually becomes dominant today. So to summarize here, really, we have a model here, the standard model of cosmology, where radiation and matter are formed after the Big Bang, so at the end of inflation. We then have a decelerated period of radiation domination and then matter domination, where we have large-scale structure, so our galaxies and our clusters of galaxies form. And then finally today, we have accelerated expansion caused by dark energy. And I should say as well, with dark energy and dark matter, we still don't really know what these are. But again, like I say, we see the effects of these in our universe. So that's our standard model of cosmology. And as I said, it's the kind of widely accepted version of the history of our universe. And it does agree well with observational data. But there are actually several problems with this model which require addressing. But the problem that I'm really interested in is the singularity problem. So this is the problem with the Big Bang being the origin of our universe. So as I said before, at the singularity, the densities and temperatures become infinite. And here actually it points to the laws of physics that we know well break down. So in particular, in our standard model of cosmology, we use Einstein's theory of gravity, or general relativity, to describe gravity. So the fact that we have singularities in this model actually point to this theory of gravity breaking down, which is actually why we want to avoid having a singularity, because singularities in general will point to a theory breaking down and not being viable wherever the singularity appears. So what I try to do is to avoid an initial singularity, and I actually try and make sure that the entire evolution of the universe can be described with Einstein's theory of general relativity. So to do this, I look at bouncing cosmologies. So there's a figure of a bouncing cosmology on slide 5. So here, instead of everything starting from this point in space and time, we actually start with a large universe. This large universe contracts and it gets smaller. We then have a bounce when the universe is at some minimum volume that's bigger than 0. And then we have a transition into an expanding universe. And that's basically what a bounce is. Now, if we consider the standard model of cosmology that I showed you, we can't actually get a realistic bouncing model to fit into that model as it is. So what we need to do is we need to look at modifying the standard model of cosmology. So I've written some notes on slide 6, but I'll kind of talk through this. So instead of having a dark energy with a constant energy density like we have in the standard model of cosmology, instead we consider a dark energy that evolves and changes with the expansion of the universe. So here, instead of being this cosmological constant, we say it actually evolves between 2 effective cosmological constants. Really, the key point to understand here is that during the expansion, so just after the bounce, the dark energy density starts off being very, very large, and is actually dominant just after the bounce, as it's here that so here the dark energy is what actually drives the bounce, so it has to be dominant around the bounce, and it has to be dominant at energy scales higher than that of inflation, so it's dominant before we have that radiation and matter creation after inflation. If you think of if we go back to the slide 4, it has to be dominant at energy scales to the left of inflation in this picture. Now, this is really because we don't want to change the evolution of the standard model of cosmology after inflation. So we still want the radiation and the matter to be produced and then have those dominant periods afterwards where large-scale structure can form. So initially the dark energy is dominant, but then what we need is for it to quickly then decrease, so that we have this radiation and matter domination, and actually we have it so it decreases quickly to be approximately a cosmological constant. a bit like the lambda is in the standard model of cosmology. And then we set this to what we observe today. So essentially what we're trying to do is we're trying to modify the behavior of the early universe at high energies to get a bounce whilst keeping the usual standard model of cosmology evolution after inflation. This is the idea here. So then moving to slide 7. Sorry, I kind of went through slide 6, but pointing you to the figure of the standard model of cosmology. So to illustrate the behavior of just the dark energy, and just to kind of try and, I guess, really show you the behavior of this dark energy, I'll show you a plot. So on slide 7, I'll kind of show you the setup of the plot. But here I'm actually showing you the behavior of the dark energy only. So there's no matter or radiation here. So essentially this plot will show us how the universe evolves and expands and contracts if we had a universe only filled with dark energy. So yeah, on slide 7, you can see the outline. So on the y-axis, or the vertical axis, we have what's called the Hubble parameter, which is denoted by H here. And this really describes whether the universe is expanding or contracting. So if it's positive, we have an expanding universe, and if it's negative, we have a contracting universe. Then on the x-axis, we have the dark energy density. So here, the vertical line that's on the right shows what we call the high energy effective cosmological constant of the dark energy. But this is basically where the dark energy density is very large and is a maximum. And then on the left, we have what we call the low energy effective cosmological constant. But this is the value that the dark energy becomes close to when it decreases to look like a cosmological constant. So really, it's the minimum of the dark energy. And the numbers along the x-axis really show you how large this dark energy density is. So when it's at 1, it's the highest, and when it's kind of close to 0, it's at its minimum. And then what we can do is we can plot the trajectories. So then I show you this on slide 8, but I'll talk you through kind of each part of the plot here. So in this plot, we consider all 3 of the geometry types that I showed you earlier. So open, flat, and closed models. Now, the thick green lines on this plot show flat models. So that was where the universe looked like the sheet of paper. Then outside the green lines, the pink and the brown curves show open models, and that was where the universe looked like the saddle. So now here, for the open and the flat models, we see that the universe either always expands or it always contracts. So if you look at the pink and brown and the green lines in the top half of the plot, they start in the top right corner, or somewhere in the top right part of that plot. Now this is where the universe is the smallest, it has the smallest volume, and the dark energy density is the largest. And then we see that the arrows point to the left. So here it shows that the universe expands and the dark energy density decreases. Now the pink, brown, and green lines in the bottom contracting half of the plot basically do the opposite. So the universe starts at its largest volume, and the dark energy density is small. And the trajectories here start somewhere in the bottom left-hand corner of this plot. The arrows then point to the right, and we see that the dark energy density increases to its maximum as the universe contracts and gets smaller. So this really shows us that if the universe is flat or open and contains only this dark energy, then we don't get a bounce. Now, inside the 2 green lines, though, we have the closed models, where that was where the universe is a sphere. And this shows a different story. So first of all, I'll concentrate on the pink and the purple lines, and also there's a very small blue line right to the left of the plot in the middle. Now here, these trajectories start in the bottom half of the plot during a contracting phase, where the dark energy density is at its minimum and the volume of the universe is at its maximum. Now the universe contracts and it gets smaller, and the dark energy density increases as the arrows point to the right. then what you see is actually the curves change direction. So now when the arrow has reached the furthest to the right it will go, where the dark energy density is at its maximum. When H is 0, we have a bounce. So at H is 0, so on the y-axis there's a 0. Essentially, when the trajectory passes this point, we have a point where contraction stops, and the universe is then neither expanding or contracting. So we kind of have this point in the middle, and that's really what the bounce is. And this then occurs when the volume of the universe is at its minimum. Then the arrow starts to point to the left, and then the universe starts to expand again. And then as the universe expands, the dark energy density decreases, and then it tends towards its minimum. So these models that I've just described, these are all models that just bounce once. We also see, though, that there's a blue oval kind of near the centre of the plot. So if we start with the bottom half of this oval, we see that the arrow points to the right. So we have the dark energy density increasing as the universe contracts. And then as before, when we have h, that Hubble parameter equals 0, we have no expansion and no contraction, and the universe bounces at its minimum volume. Then the arrow points to the left, the universe expands, and the dark energy density decreases again, and reaches a minimum when this line is at the furthest point to the left, and this is where the universe is at its maximum volume. There's then this point where, again, the expansion actually stops, and we pass h equals 0 again, and the line changes direction, and the universe recollapses. So this is really a point where the expansion stops, and we call it a turnaround, and then it starts to collapse again. And they're actually then repeated cycles. So then the universe actually contracts again, it bounces, it expands again, and then recollapses, and so on and so forth. And we call these cyclic models. So you have lots of bounces, essentially, rather than just one like the other curves. So really the takeaway message here is that when the universe is closed and spherical, containing only this dark energy, all of the possible models that are closed have a bounce. So this dark energy always produces a bounce when the universe is closed. Now, this is good, but we know that dark energy isn't the only part of the story. So as I mentioned before, dark energy isn't the only component in our universe. So now looking at slide 9, this is really where my research comes into play. So my research focuses on then including matter and radiation to this setup with the dark energy. And there are kind of 3 questions that we want to ask. The first question is to see if we still always get closed bouncing models when the universe is closed, if we include dark matter and radiation produced after the bounce. So a bit like in the standard model of cosmology, where radiation and matter are produced at the end of inflation. And the question really is here, is the bounce spoiled when we include matter and radiation, or can we still always get closed bouncing models? The second question is whether we have a decelerated period where matter and radiation could become dominant, so we still have our usual evolution where we get our stars and our galaxies and our galaxy clusters form, like we do in the standard model of cosmology. And then do we also get a late time accelerated expansion like we observe today? So then finally, I mentioned earlier that this dark energy needed to be dominant at energies higher than that of inflation before the radiation and matter are created, and then decrease quickly to be close to what we observe today, so that we still get the standard model of cosmology evolution from kind of the radiation domination period onward. So the third question then is really whether or not we can say yes to question 1 and 2 when the dark energy is initially dominant before radiation and matter are created, and then subdominant until kind of recent times where it will become dominant again, so we get this accelerated expansion. So once again, really to investigate this, we need to make a plot to understand how the universe evolves when we have this dark energy, the matter and the radiation. So on slide 10, I show the outline of this plot again, and this is similar to before, just with a couple of changes. So again, on the y-axis or the vertical axis, we have the Hubble parameter, which describes whether the universe is expanding or contracting. So when it's positive, we have that the universe is expanding, and when it's negative, the universe is contracting. Then on the x-axis or the horizontal axis, we have the dark energy density. So again, the vertical line that's on the right is where the dark energy density is a maximum. And now we also include the energy densities of dark matter and radiation, which are also a maximum on this line on the right-hand side. Then we have the vertical line on the left-hand side. And again, this is where the dark energy is a minimum. And here dark matter and radiation are also at a minimum. And actually they're 0 on this line. So then now looking at slide 11, we can again plot the trajectories as we did before. So as it was last time, the green lines in this plot show the flat models where the universe looks like the sheet of paper. And then the brown and pink trajectories outside of the green lines are the open models where the universe looks like the saddle. Now, similarly to before, the open and the flat models either always expand and the energy densities of the dark energy, dark matter and radiation all decrease, which is seen by the lines in the top half of the plot that all, the arrows all point to the left. Or we have open and flat models always contracting, and the energy densities of the dark energy, the dark matter and radiation all increase, which is shown in the bottom half of the plot where those pink and brown trajectories point to the right. But our focus is really on those closed models inside the green curves. So as before, we have cyclic models, which is shown by that pink oval kind of near the centre, where the universe contracts and the energy densities of the dark energy, the dark matter and radiation will increase. The universe bounces at a minimum volume and then it expands and the energy densities will decrease. And then the universe reaches the maximum volume before recollapsing again, and so on and so forth. All of the other closed trajectories start in a contracting universe. They bounce once and then re-expand. So they start in the bottom half of the plot, the arrows point to the right and the energy densities will increase. They bounce and then they re-expand and the energy densities will decrease as the arrows point to the left. So to answer our question 1, if we include radiation and dark matter produced after the bounce, then yes, all closed models bounce, which is good. That's what we were hoping for. So the next question was to see if we had models that have a decelerated period where large-scale structure, so our galaxies and galaxy clusters, can form like in the standard model of cosmology. So on slide 12, you'll see the same plot, but I've added 2 vertical red lines. So these show where the acceleration is 0. So between these 2 red lines, the universe is decelerating, and outside of these 2 lines, the universe is accelerating. So here the models that we're really interested in are the purple and the orange curves in the plot. So the ones that are kind of the biggest, longest lines between those two green lines. So these are models that bounce once, and we see that after the bounce in the top half of the plot during the expansion, where the arrows point to the left, these models are initially accelerating. They then cross the first red line and they decelerate. And here this is where we could have our large-scale structure, our galaxy clusters form. And then the curves continue to the left and cross the next red line, and then the universe accelerates again like we see today. So then to answer our question 2, yes, we can have a decelerated period where we could have our structure formation in these models, and they can also produce the late time accelerated expansion like we see today. So then the final question was about dark energy being dominant at early times at high enough energy scales, and then decreasing so that radiation and matter could be created and can be dominant. And at late times, so after it's initially dominant, it would look like a cosmological constant from that point onward. So this is really a question of whether the maximum and the minimum of the dark energy differ by enough. So on slide 13, I show a plot where the maximum and the minimum of the dark energy differ by this much. So on the right-hand side, the vertical line, the dark energy is at an energy scale higher than that of inflation, And then the vertical line on the left, the dark energy at its minimum is close to what we observe today. Now we find that all closed models bounce, which is good, but they always accelerate. So we don't have a decelerated era where we can have structure formation. So then in response to question 3, no, we can't have realistic bouncing models where the dark energy is initially dominant before a radiation dominated period, which then decreases to close to what we observe today. So essentially what this means is that we find that we can only have a bounce with a decelerated period when the bounce occurs at energy scales far below that of the radiation and matter dominated periods, which would mean that we would have a bouncing universe where we don't have high enough energy scales for radiation and matter to be created as they are in the standard model of cosmology. So we find that these models aren't actually feasible. In general, though, we do think this is kind of a good framework to work off of. So even though the specifics here don't necessarily work realistically, because we can find that the behaviour of the dark energy with the dark matter and radiation in general can always have or always produce a bounce for closed models and have that decelerated period. We think maybe we could kind of try and tweak this model to see if it would work with kind of a more realistic dark energy evolution. So I think with that, I'll leave you with my conclusions on slide 14. And this really just shows a summary of the answers to the questions that I asked in the beginning. But yeah, no, I'll thank you for listening, and I will take any questions.
Thank you so much, Molly, for this really amazing presentation that you guided us through your work and also explained really well the principles and basically the background of your work, and it was really interesting to learn about it. So yeah, please flash your microphones if you have questions. Post questions in the chat, and we'll go from there. So yeah, Rafael, if you have a question, please go ahead. We'll start with the more general public ones, and then later on I'll go maybe a little bit deeper. Thank you.
Thank you, Katerina. My question is, I'm coming from I have zero knowledge about this. I think you might have heard about something that is discussed called meta-humans in sci-fi shows. And they discuss a lot based on what you have been discussing, like dark matter, dark energy. My question is, to me, it seems based on what I understood, and I understood very little because I don't have the background requisite knowledge about this, but thank you for your information you presented. Are metahumans possible in the future, 500 years, 1,000 years? Thank you.
So I'll be very honest, I don't I've not heard of this. Do you know what what's was it for? You said from a sci-fi show?
Yeah, so what happens is these are humans that interacted with dark matter and got supernatural powers. So somebody could run really fast, like there's a character called Flash. But the concepts that they base it on are exactly similar to what you were discussing. So that's why I had this question in mind.
Okay, I see. As much as I would love that to be true, I don't think that's realistic. I mean, essentially, when we're looking at dark matter, we're kind of looking at it with either kind of experiments that we send up into space, or kind of ground-based observations. So it's not something that we're physically touching. It's something that we try and look at the effects of, and we're not really sure what dark matter or dark energy exactly is. We have a lot of unanswered questions, but But I would love that to be true. Unfortunately, I don't think it is. But yeah.
Okay. Thank you, Molly. Thank you. I appreciate it. Thank you very much.
Thank you.
I got a question real quick, if that's cool, Katarina.
Yeah, go ahead.
So, I don't really know too much or anything about like cosmology, but I like watch a lot of YouTube. So, what I was kind of curious on is if like your model could include maybe like some type of repulsive between like the radiation we know of and like dark energy itself, whereas like maybe like as matter like emits like radiation in general that it there's a repulsive for like relationship that kind of keeps pushing like dark energy out, expanding the universe versus just an expansive like nature to dark energy. I was kind of curious about that.
Okay, so I think I understand the question, but let me know if I answer something that wasn't what you were asking. So in this case, kind of in general, assume that each component, so the radiation, the dark matter, and the dark energy, kind of all evolve independently, roughly speaking. But you can actually look at models where all of the components actually depend on each other, which means that they kind of have what we call an interaction between them. So it means that the evolution of one fluid depends on the evolution of the other and they influence each other. I hope that kind of answers the question.
Yeah, it makes sense. So like you don't make your models where these two have a relation, like you kind of keep it as kind of like independent from each other.
Yeah, in essence, yeah, they don't have any kind of like direct interaction with each other. They're all independent from each other, kind of in essence.
Interesting. Thank you.
Yeah, Akil, did you have a question before I go into questions?
Well, I'm currently like in another meeting. I'll be free in about 20 minutes or so. If you guys are still around, I'll ask my question. But right now, I'm a bit busy. I'm sorry.
Oh yeah, don't worry about it. Yeah, that's why we record these sessions. So I know that if you're in the US, it's kind of in the middle of the day in the morning, so a lot of people are also working. But thank you for being here for sure. And so we've been discussing like a more broader um, basically topics related to this. So I will maybe go into a few questions that I received ahead of time and had also myself. um, so if you could go, let's start broad into the significance of this bouncing and cyclic cosmologies, and what this means basically in for what this means for the general understanding of our universe, and so will this be going on endlessly? Like, will this be an endless loop, you think? Or based on your description of your models, did we have previously a lot of bouncing going on, or is your prediction a more that this is just a few times maybe, or maybe just one time? If you could go over that one again, thank you.
Yeah, sure. So, I mean, there are lots of bouncing and cyclic models in the literature, and really whether it happens once or it happens multiple times really depends on what model you're working in. So for my research, actually, the cyclic models aren't really we kind of always knew weren't feasible from the get-go, and this is for two reasons. One is because they don't they initially accelerate and then decelerate, but they don't accelerate again, so we can't actually, in the context of my research, you can't actually get the accelerated expansion that we observed today. It was really the models that just bounce once. So you literally only ever have one bounce. You start with a large universe, it contracts, it bounces, and then it re-expands, and then that's it. Obviously, these don't really work realistically, but those are really the models that that we were kind of most interested in for kind of most of this project. Maybe I should say, though, in the wider context, though, yeah, like I said, you can have models that just bounce once. There are cyclic models that you'll have several bounces, so you have several cycles of like an expansion, then a contraction, a bounce, and an expansion, and so on. So, for example, you can get a case where actually the volume of the universe increases with each cycle, and eventually then it stops collapsing. It basically gets to a volume that's big enough, and we have the accelerated expansion that we see today, and you never recollapse. So this is really, actually, it's an open question in the field, is if we do have a bounce, how many times do we have a bounce? But no, it's a really interesting point.
Yeah, so there's a big difference, right? If you assume that this is a closed model, then the likelihood increases for a singular bounce, as far as I understand, right?
Yes.
It's a different, right? If you assume it's a closed model, then a singular bounce is more likely, right?
Yes. Yes. So yes, so you can kind of see, so if we look at I'm looking at slide 11, you see that actually the chance of the universe being cyclic is actually very small in this case anyway. It's also, I think I just said that there were two reasons, and I think I only gave you one, that as to why we don't have or we didn't think the cyclic models were good. It's also because you'll see that the lines, so like the orange line, for example, in this plot becomes very, very close to this green line, and that's really what we want, because we know that the universe looks close to being flat at the very least, which doesn't really happen with the cyclic model. But I mean, we also if we were considering, kind of regardless of where the trajectories were in the plot, if we were considering all of these models, then it would be least likely to have a cyclic model. You would kind of need quite particular initial conditions. So yeah, if we were considering all of these closed models, you would the cyclic models only make up a small part of the plot, so they would be less likely. But there's kind of other reasons why we don't really favour them in this scenario anyway.
Yeah, that's interesting. Related to that, I had a few questions, but so is the relationship or the ratio basically of dark matter and its radiation, this does fit in the model basically for the bouncing, or isn't that relevant at all, like the dark matter content basically of our universe?
So essentially the thing that you have to be really careful of in these models is dark matter and radiation being dominant at early times, at high energies around the bounce, essentially because in if they're dominant, you actually don't get a bounce. So in the context of bouncing cosmologies, really okay, so there's kind of two important things. Number one, the observations today and your theory kind of need to match. But if you want a bounce, you also need to make sure that the dark energy is dominant at energy scales higher than the matter and the radiation were created. Otherwise, you get a bounce at scales. So either you get a bounce at scales lower than the dark matter and the radiation were created, so then you wouldn't have them in your model, or you would have a case where you don't get a bounce at all. So you would have a singularity in your model, and again your model, the physics in your model basically breaks down. So really the goal here, the plot I showed you with just the dark energy, that was kind of the starting point of what we were looking at. So we knew that this dark energy in itself can always produce a bounce when the universe is closed. Really what we wanted to find out was whether including dark matter and radiation spoilt the bounce. So it's kind of in terms of the bounce, their energy scale where they're created is really what's important here, because we need to make sure that they're not dominant. Otherwise, we don't get a bounce.
Yeah. Yeah. Thank you for re-explaining those. And my question also was about entropy. As far as understood, at some point, kind of our universe runs out of it. So basically, at some point, there's no way to go anymore. Does this bouncing back kind of reset entropy states, or is that why also, is that another factor why you can only basically the only one time bouncing is the more probable scenario?
So I didn't really explicitly look at entropy here, but actually there's the cyclic scenario that I was telling you about, where the volume of the universe increases. I think, okay, if I remember correctly, I think that was a scenario where they looked at entropy as well, and essentially you get to a point where I think maybe there's kind of a point where you can't recollapse because of that. But I'll be honest with you, I don't remember all of the details. But in the context of this research, that's not really a factor. But saying that, when you look at an analysis like the one that we've done, it's very much looking at the general behaviour. If we found models here which were kind of worked theoretically in this framework, we would then be looking more at observations and kind of more details like that. So here we don't really say anything about that, but that's not really why the cyclic models are disfavored. But I'm really trying to remember. It was a while ago. There is research into entropy and like bouncing or cyclic models and how many cycles you can get.
Yeah, interesting. Yeah, thank you. We'll make sure to look it up, and if people have this question, we can share it then later on. And does this model basically and your findings, do they change the understanding of any basic physics? So for example, the quantum field theory, is there an impact on that we have to kind of think over some physics laws, or is this I think you already kind of discussed it, but just to point it out for the audience again, if like understanding of current physics laws are impacted by your findings.
So yeah, you bring up a really interesting point about quantum field theory, which we discussed quite a lot in the paper, but I actually didn't discuss too much here. So maybe just to start with a bit of a background of what we're talking about here is in this standard model of cosmology, so where we have that dark energy being a constant energy density all throughout the universe, we can actually observe its value today. So we observe what I called lambda, which is this dark energy density. Now we have a theory which is called quantum field theory, which basically predicts a contribution to what we should observe today. Now, what we observe is very small, and what quantum field theory is telling us should be contributed to this observation is very, very large. And we call this the cosmological constant problem. So it's really this discrepancy between theory telling us one thing and observations telling us something else. And we don't really know how to resolve this problem. We don't know how to kind of counteract this really big contribution from this theory. Now, in the setup that I have here, essentially it wasn't really what we were intending to look at necessarily, but it kind of became a natural outcome of the setup. So because this dark energy density starts really large and then it decreases and becomes close to what we observe today, so it becomes much smaller, and because of the kind of energy scales that we're talking about, we kind of have a way of explaining this problem if our model worked. So really we were kind of hopeful, and then it didn't work anyway. But if we're talking about the kind of maximum energy of this dark energy being kind of energies higher than that of inflation, so really high energies in the early universe, this kind of would explain why we get this really big contribution from quantum field theory, and then it would decrease to what we observe today. So it would kind of link the two values that we get, but because that's kind of the specific point that actually doesn't work, because we don't have the right evolution when our dark energy evolves over those kind of scales. That hasn't really changed our understanding, but it's kind of a really it's a nice kind of perspective, like a different angle, I guess, to take on it, rather than trying to explain or trying to counteract this kind of large contribution that's predicted from this theory.
Yeah, that is really interesting, and thank you for your answers. And what maybe one of the last questions is what are you working on now, and what is the future you want to work on? Like, where's your research taking you basically right now? So thank you.
Yeah, so really carrying on wanting to try and avoid having a big bang or a singularity as the origin, and having like a bounce, whether it's once or whether it's lots of times. Really what I'm looking at now is actually we kind of touched on this earlier, but having kind of each of these, like the dark matter and the dark energy, actually interacting with each other. So the two of them would depend on each other to evolve throughout the universe, and seeing if we can get these bounces or these cycles. And I mean, really, like the ultimate goal, like if I could, not that you can choose and research where you get to, because research isn't research isn't as compassionate as that, but it would be really cool if we could get a model that we could actually start constraining with data and kind of get some predictions out that would be relevant for future observations to see if we can distinguish between whether we had a bounce or whether we had something different. So yeah, that would be really cool.
Yeah, that sounds like a really exciting future, and I'm really looking forward to follow your work in the future. And talking about future, if you have time for one more question, I think we have a question about time travel. If that would be a possibility, like more likely in your model. And yeah, I don't know if you have anything regarding time travel or parallel universes traveling to those related to your model. If you could indulge us in like probably sci-fi type of yeah thinking.
See, I really wish I had something really interesting or really witty to say right now. Honestly, that's not something that we consider that we consider in our model. I'm assuming when you say time travel, like you want to go back or forward in time, like in Doctor Who or something. I'm afraid the physics in the model isn't relevant to that problem.
Well, yeah. So, but it's I didn't want to end with a note like it's really really interesting to learn about the principles of our universe, if if a bouncing is possible, and to go deep into those very early first second stages, and that we can learn so much about them. So yeah, thank you for sharing this research with us. And as I said, we will be really curious learning about your future research in that regard. And it's really a frontier in our knowledge that we don't, I feel, have so much in our everyday life. So yeah, congratulations of choosing such an exciting career, and we wish you all the best for the future.
No, thank you for inviting me. It's a really cool. I think I said this to you when we spoke the other day. This is a really cool way of doing, like, having public talks.
Yeah, thank you. Yeah, hopefully you'll join us again. And thank you everyone for sending in questions and for asking questions and participating in the discussion, also for future listeners. Yeah, I think it's a very positive way of discussion, because it kind of gives us hope for the future. So thank you, Molly. Thank you, everyone. I hope to hear you all again soon. Yeah, I'll close the room now in 3, 2, 1. Thank you, everyone. Bye.